Let's talk about some properties of logarithms. And I know that we've already discussed some properties here in this course regarding logarithms, but I wanted to go a little bit further and discuss the product, the quotient, and the power properties. And to start off, I want to remind you that logarithmic functions are simply inverse functions of exponential functions. So it would make sense that the properties of exponents should have matching properties with logarithms. So let's take a look at an example of this. So for example, suppose we were looking at 2 to the 5th power. Well, we know that 2 to the 5th power, all of this is simply equal to 32. But we also know that we can rewrite 2 to the 5th power as a product of two other exponents. That is, 2 to the 3rd power, for example, times 2 to the 2nd power. Because we know that 2 to the 3rd is equal to 8, and 2 squared is equal to 4, and multiplying these also give me 32. So the exponent property, the product property for exponents, said that, hey, if we're multiplying two exponents that have the same base, this is equivalent to adding those powers. We can also do that, where this is 2 to the 5th power. So again, if there are properties for exponents, it should follow that there are properties for logarithms. So what would that look like? So let's first write 2 to the 5th power is equal to 32. Let's write this in logarithmic form. So we would say log with a base of 2 of some value is equal to 5. Well, what is that value? 32. We know that this is equal to 5. So I just took that exponent and I wrote it in logarithmic form. Well, what would be the matching or corresponding logarithmic property then? Well, we could say, since we know that 5 is equal to, in this case, 3 plus 2, I want to come up with a logarithm that's equal to 3. So with a base of 2, log base 2 of what value is equal to 3? Well, this would be log base 2 of 8. This is 3. And here I want to go ahead and add to it log base 2 of what value gives us 2, or this number here. Well, that would have to be 4. So the matching logarithm property says when you have an argument here, when you have an argument that can be rewritten as a product of two factors, then you can actually rewrite that entire logarithm as the sum of two logs with the same base, such that these arguments equal 32 when I multiply. Let's write this in general form, and I think hopefully it'll be a little bit more clear. We could say log base b of some argument, and if that argument is the product of two factors, we can rewrite this logarithm so it's log base b of x plus log base b of y. And again, if you think back to why we're allowed to do this, remember, logarithms are simply the inverses of exponential functions. So we have exponent properties that say if you're multiplying two exponents that have the same base and saying that that is equivalent to adding those powers, we can do that in logarithmic form, where we are multiplying the argument, or we're multiplying two values to give us the argument, and that's equivalent to splitting up that logarithm as a sum of two logs with the same base. So I won't work through all of them, but you can kind of get the idea. We know that, for example, with the quotient property, if we said 2 to the 5th divided by 2 squared, well, the quotient property for exponents say that that is equivalent to 2 to the 5th minus 2, which is 2 cubed. So for the logarithmic property, we would say if our argument is the quotient of two numbers, then we can rewrite this as log base b of x minus log base b of y. Okay? And what about the power property? What does the power property say? Well, the power property says something along the lines of if you have something like 2 cubed and you square all of that, well, we know that that is 2 to the 6th. What do we do here? That's equivalent to, I should write 3 times 2, which is equal to 2 to the 6th. Well, what would this be in logarithmic form? So something like log base 2 of, log base 2 of 8 here squared is equal to the same thing as taking that 2 and multiplying it, right? This would give us here, all of this would be equal to 6. Log base 2 of 64 is equal to 6. which is the same thing as multiplying 2 by log base 2 of 8, which is 3. So the log property here would say we can take this power of our argument and multiply. So we have, we would have y log base b of x. And there are also corresponding natural log properties here. So natural log of xy, natural log of x over y, and these are effectively all the same. This would just be ln of x plus ln of y, ln of x minus ln of y, and y times natural log of x. Okay? All right. So hopefully that makes sense if you just, again, continue to remember that these are the inverse of the exponent properties. So with that said, let's try a few practice problems here. So first off, let's look at this first set of examples where we are going to rewrite these logarithms in terms of natural log of 2 and natural log of 3. Well, first off, how can I rewrite 6 in terms of 2 and 3? Well, this is equivalent to natural log of 2 times 3. And our property would state that we can then expand this as the natural log of 2 plus the natural log of 3. Okay, well, what about number 2, natural log of 2 over 27? Well, we know that this can be rewritten as natural log of 2 minus the natural log of 27. And then how would I rewrite that 27 in terms of 3? Well, this would be the natural log of 2 minus the natural log of 3 cubed. And again, using the power property, we can then rewrite this as a natural log, 3 natural log of 3. So whenever we're expanding, we're going to want to move our powers to the front and rewrite them as coefficients or factors. When we are condensing or writing it as a single logarithm, we're going to want to rewrite those factors as powers of our argument. Let's try a verifying problem, and this is a pretty straightforward verifying problem. What about something like this where we have two sides, and to verify means we want to show that these two sides are always equal to each other without performing any operations to both sides. So we're going to work exclusively on one side. So this left side here, we can say log base 10 of 1 over 100, and I'm going to move that power, and I'm going to reverse it. I'm going to go back and move it as or rewrite that factor as a power of our argument. So this is to the power of negative 1. So that's the case. Then this 1 over 100 to the negative 1 power, raising something to a negative power, just flips it, rewrites that as the reciprocal. So that is how we would write that one there, and that is fully verified. We've showed that both sides are equal. Okay, let's try some problems where we want to do some expanding. We see that log base 2 of 3xy, we're going to want to expand this out. That is to say, we're going to break it up into the sum, or rewrite it as a sum of a bunch of logarithms. So since we are multiplying 3 factors here in our argument, I can then write this as log base 2 of 3 plus log base 2 of x plus log base 2 of y. Okay, let's try this next one. Well, this time we have a quotient for our argument, so clearly we can write this as the natural log of 4w minus the natural log of 7p. However, we can continue to expand this because we've got an argument here that is the product of 2 factors. So we can then write this as the natural log of 4 plus the natural log of w minus the natural log of 7, let's put all this in parentheses, plus the natural log of p. But we're going to want to distribute that negative, so we're going to say make this negative 7 and make that negative natural log of p. And finally, this next one here, we've got a couple of properties that we're going to be employing here. So first off, let's start with the quotient property. So log of y to the 7th x squared minus log of z to the 5th. So that splits up the quotient. Now I've noticed again that I've got logs with arguments that are the product of 2 factors. So I'm going to write this as log y to the 7th plus log x squared minus log z to the 5th. And finally, we're going to take care of all these powers. We're going to rewrite all these powers as factors. So 7 log y plus 2 log x minus 5 log z. Okay. All right, so we've got some practice problems here. I'm not going to go through all of these right now, but there are a few that I do want to touch upon. So let's jump to something like number 1 here, where we're going to condense a logarithm. Okay, we're going to condense this logarithm because this is the opposite of what we just did. We're going to rewrite this as a single log. Well, we're just going to kind of work this left to right. So we have log base 5 of x minus log base 5 of y. Note that this is not the same thing as this. So we're not putting y plus 2 as our argument of our log. So we're going to say log base 5 of x over y if you're subtracting those two logarithms. Now, what about this 2 here? Well, to fully condense this, we're going to want to rewrite this 2 as a logarithm with a base of 5. So, in other words, I'm asking myself, if I want to write this with log with a base of 2, what would this have to be? Excuse me, not base of 2, base of 5, excuse me. Log with a base of 5, what would have to go here such that all of this is equal to 2? Well, 5 to the second power is 25. So we can rewrite 2 now as log base 5 of 25. So we're adding log base 5 of 25 to this. In which case, this is simply we can combine these two logarithms using the product property and write this as 25x over y. Okay, let's try something like number 2. Let me just get this out of the way. Number 2 is a good one. So how would we condense this? Well, there's a couple of ways that we could do this. And what I think might actually make our lives a little bit easier is if I move that 2 and rewrite this entire logarithm as such, right? Because if you're dividing by 2, you're effectively multiplying by 1/2. Next, I'm going to rewrite that 1 in terms of log base 9. So again, log base 9 of what value is equal to 1? Well, that would have to be 9. 9 to the 1 power is equal to 9. So I'm going to rewrite that 1 as log base 9 of 9 plus log base 9 of x, which means I can then rewrite this as log base 9 of 9x. Now I'm going to take this factor or this coefficient here and rewrite it as the power of just my argument, not of my entire logarithm. So actually I should have rewritten this. This should look like this. It's going to be the power of just my argument. That is to say, all of this would be 9x to the 1/2 power, or we could say the square root of 9x. And this can be further simplified just to write this as log base 9 of 3 root x. Okay. Now, I do also want to highlight that there is another way to do this problem, okay? So hopefully you wrote this down. I'm going to delete it right now or erase it so I can make some space for my next one. You could also do the problem as such. I'm going to do this in a different color. I'm going to rewrite each of these constants in terms of log base 9. So log base 9 of 9, which we already said, plus log base 9 of x. All of this over log base 9 of 81, because 9 to the second power is 81. Now I'm going to condense this, log base 9 of 9x over log base 9 of 81. Now we are not done. This is not a single logarithm. We're actually dividing two different logarithms. But I want to ask you, is this the same thing as this? And the answer is no. We just said with our properties, we know that this log base 9 of 9x over 81, that this is actually equal to log base 9 of 9x minus log base 9 of 81. So if we were to say that these somehow are equal to each other, then we're saying that dividing two logarithms is equivalent to subtracting two logarithms, which is certainly not the case. So these are not equal to each other. So I'm going to actually erase all this, okay? So then the question remains, how do we rewrite this as a single logarithm? Well, I want to remind you about the change of base formula, which said that log base b of x is equal to log of x over log of b, okay? Well, if that is the case, then if this is the case, then what we see here is that it doesn't matter what our base is for each of these. What does matter is that we have the same base in the numerator and denominator. That is to say, we can also write natural log of x over the natural log of b. These are equivalent here as well. So if that is the case, look at what we have here. Can I rewrite this using the change of base formula? And yeah, this would be equal to log base 81 of 9x. These would have to be equivalent there. Okay? All right, well, hopefully this has helped. I'm going to go ahead and just try one more problem just to really finish this off, just to make sure that we're solid with this stuff, and you can try to work on the rest of this stuff on your own. We could try something like this one here. Let's go ahead and condense this one. So I'm going to say this is log base 3 of 8 squared. I'm going to take this 2 and write it as a power of my argument, plus log base 3 of z to the 1/3 power, minus log base 3 of x plus z to the 3rd power. I know I can write this as a single logarithm. And since I'm subtracting all of this, I know that I'm going to divide all of this by x plus z cubed. Okay? All right, so hopefully this has helped, and make sure that you also watch my video on the change of base formula to make sure that you are solid with that as well.